If someone asks, "Hey, can you tell me the average of the numbers?" a mathematician might jokingly say, "Which mean do you mean?" Most people are referring to the arithmetic mean, which is the most common simple average. But in some applications, other means may be more appropriate. For example, the geometric mean is useful to calculate the average annual growth rate, and it's used in economics, for example. Then there's the harmonic mean, which is useful to calculate things like the average speed. There's also something called the root mean square, which is useful in electrical engineering, and it's also called the quadratic mean. Interestingly enough, there is a relationship between all of these means. It's abbreviated by their acronym, the RMS, AM, GM, and HM inequality. This is useful in math competitions, and it's also useful in theoretical proofs. In this video, I'm going to present the version for two variables because there's a nice geometric visualization of it. So first, let's state it. For positive numbers a and b, the largest quantity will be the root mean square. This is equal to the square root of the quantity a squared plus b squared all over 2. This will always be greater than or equal to a plus b over 2, which is called the arithmetic mean. This will always be greater than or equal to the square root of a times b, which is the geometric mean, and this will always be greater than or equal to 2 divided by the quantity 1 over a plus 1 over b, which is the harmonic mean. Furthermore, equality holds if and only if a is equal to b. So this seems like an extremely complicated statement, but we'll be able to demonstrate why this is true geometrically. So let's get started with the geometric construction. We start out with one length of a and another length of b. Now we construct a semicircle with diameter a plus b. Next, we construct a radius of this semicircle. Notice it has length that's half of the diameter, therefore it will be a plus b over 2, which is the arithmetic mean. Now let's construct the root mean square. This segment right here is equal to the length of the radius minus the length of a. This will be b minus a all over 2. Now suppose the vertical radius is perpendicular to the diameter. We now construct the hypotenuse of this right triangle. Using the Pythagorean theorem, we can figure out its length. It will be equal to the root mean square, which is the square root of the quantity a squared plus b squared all over 2. From this diagram, we can see the root mean square will always be greater than or equal to the arithmetic mean because the hypotenuse is never smaller than one of its legs. Now let's construct the geometric mean. We'll construct a perpendicular where the two line segments meet. Now a triangle inscribed in a semicircle is always a right triangle. So we've constructed an altitude on a hypotenuse of a right triangle. Using those properties, we can deduce that the length of the red segment is equal to the square root of a times b, and this is the geometric mean. Now let's construct the harmonic mean. But before we do that, let's relate the geometric mean to the arithmetic mean. We'll construct a hypotenuse from the top of this red line to the center of the semicircle. The hypotenuse is a radius of the circle, so its length is equal to the arithmetic mean, which is a plus b over 2. And from this diagram, we can deduce that the arithmetic mean is always greater than or equal to the geometric mean. So now let's construct the harmonic mean. We'll draw an altitude to this hypotenuse. Using the properties of an altitude on a hypotenuse, we'll try and figure out the length of this purple segment, which we'll call x. So using these similar triangles, we get that the geometric mean squared is equal to x times the arithmetic mean. We substitute in those values and then solve for x. Another way of writing this is 2 divided by 1 over a plus 1 over b, which is exactly the harmonic mean. So now, from this diagram, we can deduce the geometric mean is always greater than or equal to the harmonic mean. So now let's put all of these lengths together in the same diagram. We can compare the lengths geometrically. We have that the root mean square is greater than or equal to the arithmetic mean. We also know the arithmetic mean is greater than or equal to the geometric mean. And then we have that the geometric mean is greater than or equal to the harmonic mean. This is all because the hypotenuse of a right triangle is greater than or equal to either of its legs. We can combine all of these inequalities together, and we have the root mean square, arithmetic mean, geometric mean, and harmonic mean inequality. Voila! But we want to see what happens if A is equal to B. Obviously, if A is not equal to B, then we have strict inequalities because the hypotenuse of a right triangle is strictly larger than the leg of its triangle. But now, what happens if A is equal to B? Do we get that all of these lengths are equal to each other? Well, let's once again visualize this geometrically. Here's an animation of B approaching A that I made with the Desmos calculator. I provided a link to desmos.com in the video description. Let's see what happens as we make the length of B approach the length of A. Notice how all the lengths are converging to the same value, and when B is equal to A, they all are exactly equal. So this illustrates that the inequalities become equal if A is equal to B. So to put this all together, we've demonstrated the root mean square, arithmetic mean, geometric mean, and harmonic mean inequality for two variables. An equality holds if and only if A is equal to B. This is the inequality for two variables, but it actually generalizes to n variables in the following form,